here is, you can see it has pretty much the same MIPS implementation, and it added onto it is a calculator. Oh, all right, good. It's a calculator, and I just determined the clocks. Now, it takes a fairly long time for each operation to run because it takes about eight clock cycles for each instruction to be read, and every keystroke has several instructions. So just doing 1 + 1 takes a bit of time, and you can see it. Now, the 27th register is the register that tells the computer, that tells the program to execute a keystroke, and the 26th register, which is now set to 1, tells it to which key has been instructed, so it knows which subroutine to execute. So now you know that it's all on hex, and so 1-1 is 17, which means that it's equals. That's the equals routine. So we should be getting an answer soon.
Depends on the field you're talking about. Work is.
Anyway, that's it, and it should work, but it didn't work this time. So I don't know. And next is Akshat. Good work.
Yeah, it only goes to show. I mean, we do stand on the shoulders of giants in computer science, and the giants are buggy. So we've got a computer simulator and we've got a computer implementer on it. The next step is upgrading that computer. And my project was in cache simulation using DLSim, trying to see the numbers behind how efficiently the computer is working. So cache memories, they bridge the gap between memory and CPU. Registers on the CPU are really fast to access, and stuff that's in memory is really slow to access. In order to make programs run faster, most modern computers use a cache which stores values intermediately for faster access. So say your memory would be something like 2 gigabytes, but your cache memory is like 2 megabytes or 4 megabytes. And the cache memory stores frequently used data, so that it can be computed faster. But the problem with building a cache is how do you decide what part of the program is more urgently needed? And there are two different schemes and a hybrid scheme for designing caches. So you have direct map cache, which is kind of like a democracy where each memory gets divided up into blocks, and each block gets a row reserved in cache. And fully associative is when you don't have any reservations, and anytime something gets accessed through the memory, it gets remembered, and you cache things as you go. And the hybrid of that is where you reserve multiple blocks, multiple rows in your cache for each memory block, and it's associated within that. We're going to look at cache soon. So one thing to remember, the main number we're looking at with caches is hits and misses. A hit happens when you ask the cache memory for something and it already had that in the memory. And a miss happens when it did not have it in the memory and it had to go and ask main memory for that for that value. So the setup that I used with DLSim was, so we already have DLSim, of course. On top of that is the plugins API, which lets you create little chips, but describe them using a Java program. The MIPS processor that we looked at, that Mr. Ronson made, and plugin reflections, which is a new feature which lets plugins talk to each other for passing data. In this specific case, it's used for collecting statistics on how well these plugins are working inside DLSim. The next step, well, actually before that. So I'm going to load up my cache program. Oh. Okay, so this is my little upgrade. I'm going to load up a program into this that will take an array from memory and sum up the array. If everything goes well, we should see a 90 in the output console. What the cache simulator is showing here is hits versus misses. Every time there's a miss and the cache memory had to read something from the data memory, it gives us a miss. And every time the computer asks for a value from memory that the cache already had, it gives you a hit. This bar here shows the percentage of memory reads that were hits. So 15%, that's a pretty low number. It shows, yeah, we need to optimize something. But it shows that 15% of the time this cache memory was asked for something, it already had those values stored in memory and it didn't have to ask data memory. And the other 85% of the time it had to query data memory. And there we go. It's got a 90. Another thing, and this cache is the usefulness of this is that I can change the kind of cache memory I want. Usually, if you were to do this in hardware, you would actually just have to burn new silicon. But luckily, this is all simulated, so you can choose your cache to be 8-way associative. If you choose your block address size to be 0, it becomes fully associative. And if you can make it direct mapped by setting the associativity to 1 and the block address to 30, in which case it works, again, like I said, sort of like a democracy, reservations, 1 record each. But yeah, the basic idea with this is that we can, so I can change the components that I'm using on this on my computer here, and what the next step, my next step, which is why I have the future work slide. The next step is to create a plugin that can change the configuration of the cache and automatically load programs, and try out different runs of programs and collect data on the efficiency of each of these runs. And I think that's really useful for learning about computers, because we're not just looking at gates and saying, hey, this gate does that gate does that, but we're looking at the integration of a whole bunch of parts and seeing how well they work, and what the economics of computation is in that sense. Thank you.
Question. So this plug-in Java thing, how does it talk to the rest of the simulator? Are you spitting out like wire signals or registers or?
Wire signals. So it has each plugin has input pins and output pins, and in your Java program, it's just this one method that gets called every time something on a pin changes, and in that method you can work with the pins. So it's really quite transparent. Yeah. Just direct Java.
When you're evaluating your segment of the work, this last bit, when you're evaluating the impact of the cache, you suffer a penalty if you visit the cache and your request isn't there.
Yes, sir.
Right? Is that being factored in, or?
Yes, sir. That's what a miss is. That's what the miss is. A miss is when you go to the cache and didn't have the value, and it had to query the main memory for it. So that penalty. In fact, the whole measurement is for that penalty. So right now we save 50% efficiency, but this is the penalty that you're talking about.
Okay, first of all, I have to give you guys a lot of respect because I've also worked with MIPS and the assembly links and had to program ALUs and CPUs. It's not fun. But I noticed from your demonstration with the DLSim that it's actually very similar to another program that I've actually had to use, which is Logisim. I wonder if you guys had any experience with Logisim, or if you could describe any kind of
Yeah,
similarities.
we looked at Logisim. What we're doing is in some ways, I think this is much better than Logisim, because in Logisim you have the basic elements of a circuit, but you can't create custom components, and which is why if you were to implement this in Logisim, it would take like for example this ALU, would take at least 200 or so gates for implementing 32-bit. The 32-bit register, I think I'll be 60 by the time I implement this in Logisim. So
Okay.
having Java, I think, makes us better than Logisim. But yeah, that's competition.
Okay,